Okay, thank you for the introduction, Fanny. So this talk is all about preserving some of the most fundamental attributes of sketching in a computer-aided design environment. So as Fanny mentioned, this talk was done together with my colleagues, Tovi, Hyunmin, Ali, and George from Autodesk Research. So anyone familiar with this structure? This is a cathedral in Brazil, designed by a very famous Brazilian architect, Oscar Niemeyer. It's a beautiful, elegant structure. But this is how the design looked like when Oscar drew his first sketch. So what do you see? We see a set of strokes, right? But we don't know whether the strokes represent a smooth surface. We don't know whether the strokes represent the columns. We don't know any structural details. We don't know the height. We don't know the base. I bet even Oscar didn't have those things in his mind. So this is how an idea looks like in its inception. In fact, Oscar had many ideas in mind. He had plenty of possibilities. Now, in the early stages of design is rough, it's ambiguous, and there's a lot of holes into it. Now, if we try to infer 3D models from these sketches, it would be very challenging because these sketches are incomplete. But most importantly, it doesn't even make sense because even the designer haven't figured out those details, right? So as Bill Buxton says that, if you want to get the most out of a sketch, you need to leave big enough holes. And Bill continues that ambiguity creates that holes. The fact that the sketches leaves a lot for the imagination is fundamental to the process, how designers think and how designers develop their ideas. So sketches ask questions, they don't give you answers, they help us to think, imagine, fill up the holes, right? So to get the most of the sketch in a computer-aided design environment, we need to accommodate that holes. In fact, I remember almost 20 years ago, Mark Gross and Ellender wrote this paper and underscoring the necessity of capturing ambiguous intentions of computer-aided design. But we still have a long way to go. Okay, so this is the traditional design spectrum. It starts from rough sketches, and the designers converge to an idea, and then gradually moves to a 3D CAD modeling. Now, it gradually stretches from implicit representations to explicit representations, right? But fundamentally, these two representations are not compatible with each other, right? Rough sketches and CADs, they're very different. But they both have their advantages. CADs are really great for analyzing, simulating, and fabricating the design. Well, there are some prior works which try to bridge the gap between the two representations. I mean, especially in the field of sketch-based interfaces for modeling. But if you look at these works closely, most of these works have tried to eliminate the ambiguities. I mean, the assumption was that the designers have a very clear, precise model in their mind. They sketch a detailed drawing or precise drawing, and then they try to convert it into a CAD model. Whereas in our case, we are trying to see how can we accommodate the ambiguity, the goals, and incomplete drawings in a CAD environment. Also, lately, the role of computers is changing in the design process with parametric modeling, generative design, and other sorts of new machine learning shape synthesis algorithms. I mean, one of the such techniques is called generative design, where the designer specifies the high-level goals, the load conditions, and so on, and the computer generates many different variations for the users to pick from, primarily based on the principle of topological optimization algorithms. So our second goal is to see how these advanced computer algorithms play a more active and participatory role in the early stage of design, when the designers are making most of their important decisions, how to inspire them with new ideas, or how to provide them more information so that can make more informed decision. Okay. Now, how do designers think when they're working in pen and paper? What are the type of conceptual tools they use? They have physical tools like pen and paper, but they also have conceptual tools in their mind. And as Mark Buskinger wrote in his book, Drawing Ideas, the designers use these 6 conceptual tools. They're called 5 Ws and 1 H. Who is the design for, what it will be used for, where it will be used for, and when it will be used for, and how it will be used for. So these are really powerful conceptual tools that helps designer to express their design content, their design ideas. Okay, so now we'll switch to a demo to show how the interface works. Okay, So this is the DreamSketch interface. It's basically a 3D drawing interface, and as you can see, there's a 2D drawing plane. You can draw in the 2D drawing plane, which you can move and rotate in the 3D space. So we will draw a bike. We will design a bike frame. Okay. So to do that, we will bring the mannequin. The mannequin gives us a sense of scale and context. Now, to design the bike frame, we will specify the problem. What is the problem we are trying to solve in this design? So now what we will do is that we will draw the most essential components of the design. So what are the most essential components of the bike frame? So one is that there need to be a seat post. So I sketch a rough seat post there, and then I kind of extrude to give it a volume, right? So this creates an object. We call it an interface object. Then similarly, all the bike frame has a geometry for pedals, right? You see the sketches can be really rough. You don't have to worry about the precision and details. And then we create another interface object. All the bikes has a handle as well. So I'll sketch a handle here and extrude it to create a handle. And then finally, I will also sketch a rear bracket here. So we have this 4 interface object, and for each of the interface objects, I can add a bit more details into it just by adding some strokes. Like this is basically the center of the back wheel, right? And then there will be a front wheel here, something like this. But you know, these sketches doesn't need to be converted into geometry. But for each of the interface objects, if you look closer, we compute a proxy geometry, which is rendered in wireframe. Do you see the rendered for wireframe sketch style? So the idea is that, you know, all we need is a coarse approximation. We don't need the precise geometry. We don't have to burden the designer at this moment that what is the exact geometry of that interface object. Okay. So finally, I will also load an geometry from, and then I will specify a void. That means that there should be no geometry in this space. This space should be empty. All right. So now I have all the components of it. Now I specify what is the function of the design. So we'll sketch the force condition that the bike frame should be able to carry the load of the rider. It should be able to handle the forces of the pedaling. It should be also be able to handle the loads, reaction forces from the ground while it is like riding. Now, as a designer, I have many possibilities in mind. I didn't fix a specific position of the bike handle. So I can say that, you know, the bike handle could be anywhere within this space. I mean, it could be anywhere in this trajectory. Okay, so I specified a range of possible positions here. Similarly, for the void, I can say that it could be anywhere within this possibility. So I keep my minds open. So I giving it an ambiguous design problem because, you know, I'm saying that I didn't make a decision, but it could be anywhere within here. But sometimes you can also create functional constraints. You can say that so that if I move the bike frame, that also moves, right? So now this is the problem definition. I didn't actually make a decision what the bike frame should be look like, but I described what are the essential components that I'm looking for in the design. And then I also specified some aesthetic constraints with the void that I'm thinking about all these possible configurations. So the problem definition is rough, ambiguous, because it captures many possibilities. Now taking that as an input, our back-end algorithm generates optimum geometries for all these possible configurations, and we can explore all these geometries just by directly navigating through this. So this is the geometry generation is not real time, so that's why I pre-compute it, but this is how it works basically. So as you can see, I can explore each of these solutions, but at the same time, you can see the performance data for each of the bike frames, like what is their weight, what is their stress, and so on. Now, it's really important to keep in mind this, that we are not providing you solution. We are trying to give you new ideas and inspiration. You don't have to use these geometries, but they are functionally optimized. They are not existing bike frames. They are procedurally synthesized new designs that satisfy these constraints. It minimizes the volume and minimizes the weight using aluminum as a material. If you use any other material, the results would be very different. So we have designed a bike frame and using DreamSketch, and as you can see, DreamSketch brings the power of generative design in the early stages of design, but at the same time it tries to preserve the qualities of sketching. Now in this case, there is like, one design variable. That's why we have like 4 different results, because we discretize the variable into 4 different values. But if you have 2 design variables, you will have 16 results. If we have 3 variables, design variables, we have 64 results, and so on. Okay. So here are the bike frames 3D printed, as you can see. I think some of you might have seen it in the demo yesterday. And here is another very short video of the system. As you can see, the designer is trying to draw a dragon head shaped lamp holder. And again, the details, the precise details of the dragon head doesn't matter at this point of time. All you need is something coarse, something approximate. But you can see the sketches, the fact that you can sketch as free form, it significantly enhances the expressiveness of the design, right? To communicate with others or to communicate with yourself as well. So in this case, the designer is specifying a range of possible configurations for the dragon head shape, and this is the input, right? I specified, okay, this is something I'm looking for. What are the possibilities there? And our system returns all these possible solutions, which you can explore by direct manipulation. Again, the bigger the holes you leave in the problem definitions, the greater the chances for surprise. But you can also leave like very small holes in the design, then you can get more expected results there. So this is left up to the designer. All right, so the execution time, how long does it take to generate? In the beginning of the project, I was working with my colleague Ali, and he was in charge of the backend simulation. And I ask him question all the time, how long this will take to generate? How long will that take to generate? And he always had the same answer. It depends. And it really annoyed me at some time. I mean, like, just give me a range. Is it a few seconds or is it a few days? And his answer was still, it depends. Well, after going through the projects and everything and generating many solutions, I can confidently say that it really depends. So in this case, there are a few numbers here. So one is we changed the resolution. What is the resolution of the voxel generations? And what is the number of iterations? So if I run the bike frame for 30 iterations using a coarse voxel size, it will take like 80 seconds, which is 1 minute. For the same problem, if we run it for 50 iterations and smaller voxel size, like high resolution, it can take as much as 20 minutes. It also depends on your computer configuration and many other things. So this is just to give you an approximate, like what are the different factors that can play into the role. We also performed some design sessions and invited 3 designers and 3 engineers because they have a very different approach to design. Engineers are always looking for optimizations. Designers don't care about, sometimes they don't care about the optimization, they're about aesthetics. Okay. And here are some of the designs created by our first-time users. Some of them has never used 3D modeling tool. In fact, this designer, she have never used a 3D modeling tool. So when she said that I want to design a glider, I thought that was pretty ambitious. But she did a pretty good job. So this is some of that. And this is another design, a table designed by an architect. So this is the problem definition, and this is the results. Different types of results. And as you can see, the results can change significantly depending on how you set up all your design variables and everything. And again, the rendering is done in non-photorealistic manner so that it suggests you ideas, not to give you absolute answers. So I think rendering plays a very critical role in this design tools. Another table design, as you can see, she added some voids in the middle so that you can have leg rooms. So I think that was a pretty clever problem definition. And this is, again, a bike rack. This is designed by an engineer, by the way, attached to the back of your car. And these are all the different types of solutions and explorations. And this is one of the tables 3D printed. I have never seen a table like this. I don't know whether you have seen, but it's very beautiful and it's functional. Okay, traditionally the engineers are very used to of optimization tools, but traditionally this optimization tool requires to give you a number of parameters. You have to prematurely commit to a number of details which you don't want to, but you have to just to run the simulation. You have to set up all the boundary conditions, loads, set up the 50 parameters, but DreamSketch leaves the burden. You can just straight jump in, explore some solutions, and iteratively give the details as you need it. And this is one of the designers. She wanted to design a lamp, light, and then this is the problem definition she set up, and she was expecting something like this. This is something she had in mind. But this is what the system returned, which is very different from what she had in mind. But the interesting thing is that it really influenced her decision and said, okay, I actually rather have something like this instead of the previous one. So it really shows how can these computer-aided design tools can influence you to think about possibilities which you didn't think before. But I don't go into the details in the user study, but the key is that we felt, after talking to the designers and engineers, we felt that DreamSketch enables the engineers to think more like designers because it gives them the creative freedom to explore the possibilities. And also it helps designers to think like engineers because you have to think about what is the function of this design, what should it perform, the load conditions and everything. So we try to bring the form and functional aesthetics of the design together in this interface. So we see our paper as, just like early design sketches, we see our paper as asking questions, not just providing solutions. What if we could accommodate ambiguity and incompletion in computer-aided design tools? How can CAD and simulations can play more active and participatory role in the early stages of design? And how that hybrid medium look like? So I invite you to explore these questions because these are really important questions. And they will have a profound impact how we design with computer-aided design tools. Thank you.
Hi, my name is Junhyuk Lee from Kai, South Korea. First, thank you very much for your inspiring talk. I think it really is a meaningful step toward the future of design productivity.
Thank you.
And my question concerns how designers work and think and how Sketch facilitates that thinking and working process. So if I take your bike frame, for example, I think it would be most intuitive for and natural for a designer to begin by sketching the bike frame itself. But it seems in your system right now, the designer sketches everything but the bike frame, no matter how, however rough or incomplete that may be. Or if I take the architecture example, I think the architect is sketching everything but the cathedral itself. So my question is, what kind of division of role or responsibility or labor do you expect between designer and computer in the future?
Yeah, that's an excellent question. I don't have answer to all of your questions, but I can say that, it's up to designer how big are the holes they want to leave. In my case, for the bike example, I left big enough holes. But I could have easily defined interface objects and I could have easily defined some of the other details of the bike. I want a shape like this, or I want a shape like this. I could have done that using this interface, just like I have defined the other different components. I could use voids and other things to define a shape that's something I'm looking for. So again, in this case, I left big holes, but in other cases, you can leave small holes so that you can get more predicted results. Yeah.
Hi, Tim Dwyer, Monash University. Really nice work. I was interested the way that you currently interact with the optimization solver. It seems to me that you specify the constraints and then you run the solver and it goes away and comes back finally with the optimal results. Have you also experimented with more partial results? So I can imagine a type of solver that spits out incremental results, live, streaming results that gradually get better and better. And
sorry, I didn't hear. Can you repeat the later part of the question?
Yeah, so instead of having a solver that is not interactive but just simply gives you back the optimal solution, is it possible using your system to interact with with the solver as it converges. So have it incrementally streaming results, and then the interaction would become more of a dialogue with the system where you can guide it towards a solution.
That's an excellent question. So I think that's something we have considered a lot, like how do we show the progressions of the results as the solver is iterating. We actually thought about it, but we didn't implement it at this moment because it's a little bit of engineering effort. But that's some of the interesting possibilities, because we can easily interrupt the solver. So you can say that, okay, we don't want this direction to go, so you can just easily interrupt the solvers. Yeah, that's an exciting direction to go, but we're looking forward to that in future. Yeah.
Thank you.
Yeah, I'm still want to know more about the optimization time. So you just show numbers, but I want to know, for the particular case, in the particular test case scenarios, how long actually you have to wait usually? Like 1 day or a few hours? In this particular examples, you show a couple of examples here.
In this case, I can say that it's basically 2 minutes for each solution. So if there are 16 solutions, it would be 32 minutes. But if we use parallel or distributed computing, we just have to wait 2 minutes, because you can run 16 instances in 16 servers. But in this case, it's 2 minutes. And I think earlier there was like a wine rack. In this case, it was longer. I think it was 8 or 9 minutes for each of the solutions.
Oh, not hours or days.
Not hours and days, but it could take hours and days depending on the parameters. Yeah,
that's useful information. Thank you.
Okay.
Tisha Satapakdi, Carnegie Mellon University. First off, really cool project. I was wondering if you thought about applying this to objects that are kinetic, like objects that have motion.
Not yet, but that's future work. I think that takes this thing into a different level. So we have to change the optimization solver and see how these things work. So that's a future work actually.